Standard relational database architecture is built for efficiency. To optimize for prediction and convenience, these systems force complex human behavior into flat metadata tables. When we compress cognition into these rigid schemas, the nonlinear texture of human thought is simply structurally lost. User's mental model over database simplicity. Scalability here isn't about compressing data points. It is about architecting schemas that can hold paradoxical human complexity without breaking it. A forensic audit of the live database reveals a sprawling identity layer and an ingestion pipeline holding nearly 28,000 data fragments. The architecture deviates from standard SAS models, prioritizing the user's ontology over transaction speed. By reverse engineering these literal rows and columns, we can see how a psychological framework is being expressed through code. The resulting schema mirrors several theoretical models from cognitive science that have lacked a viable path to physical deployment for 30 years. We are looking at something far more than software engineering. This is a compiled operational model of human consciousness. The audit begins with the ingestion pipeline, revealing two parallel embedding architectures. On the left, a legacy sidecar pipeline hits a 511-row bottleneck, creating massive semantic blind spots. The right side shows a modern inline pipeline, routing through knowledge fragments, achieving 99.9% coverage across nearly 30,000 rows. The system uses 768-dimensional vectors to capture the specific semantic shape of every input. This process meticulously breaks hundreds of source documents into over 27,000 distinct fragments. This high resolution allows the internal AI agent to query the user's context without any loss of detail. High-coverage semantic retrieval demonstrates that engineers can maintain a user's full complexity without relying on data reduction or summarization. Moving to the identity layer, we see how the system encodes character. The foundational blueprint is a 12-module philosophical framework. These lines map the first 6 modules directly to their primary keys, making every character trait a discrete, queryable data point. The semantic foundation for the entire model is Module 11, the PLK, which documents the user's specific linguistic patterns. Most systems rely on reductionist personality types. The PLK creates a semantic fingerprint based on the user's actual speech. This fingerprint allows the system to calculate high-resolution resonance scores during a conversation. Identity in this architecture is not a static profile. It is a networked graph of mathematically verifiable fragments. In a system this complex, the primary risk is semantic drift, the slow corruption of the user's core identity over time. To prevent this, the system uses constitutional invariance, hard architectural rules that override standard AI defaults. These invariants are enforced at the database level. They act as a physical gate that blocks incoming data from altering the core schema. Any change to the identity layer is trapped in a mutation proposals table. No identity shift can be permanently written to the database without a manual human approval trigger. If a conflict arises, the identity rollback events table provides an immediate architectural safety net. Standard AI applications often overwrite user context behind the scenes without notice. Here, user memory is treated as a verifiable governance protocol. Digital identity must be treated as critical infrastructure, requiring deep structural protection at the root rather than just superficial computational processing. These architectural decisions mirror a specific lineage of cognitive science published between the 1950s and the 1990s. Researchers in this era were limited by their hardware. They lacked the software delivery mechanisms to test their theories at scale. Theorists like Carl Rogers or the authors of extended mind theory could describe these cognitive frameworks in the abstract, but couldn't deploy them. This is a case of Platonist multiple discovery, when the same underlying structure is found independently by different people approaching from different directions. Look at how the 1998 extended mind paper maps directly to the knowledge_fragment schema. The founder built this system to solve the practical friction of his own ADHD. He unknowingly produced a codebase mirroring the architecture described in those academic papers. Practical constraints in code can unintentionally validate decades of stalled theoretical models. This 100-table diagram is more than a database. It is a living cognitive architecture. This infrastructure was built iteratively by a solo engineer who was simply solving for his own necessity. The system scales because it inhabits complexity instead of resolving it. The system demonstrates that the common compression problem can be bypassed with the right architectural priorities. Right now, full-stack AI engineers are currently building the identity and memory layers for the next generation of software. This work suggests we can design ontologies capable of holding the uncompressed human signal. Human complexity can scale. We simply have to choose to build infrastructure that serves consciousness.